Hi everyone, my name is Nader Haghighipour. I'm an old PSIer. I joined PSI in 2002, a few months before Mike Sykes joined. And I stayed with PSI for quite a number of years and left PSI for Hawaii. And now I'm back. It's great to be back. It's great to see all the old timers and also some new faces. More importantly, it's great to see that the PSI has grown that much. When I joined, I think the total number of the people at PSI was only about 12 or 13. So great to be back. I was asked to give a summary of the work that I do and the research that I'm currently involved in. Fortunately, I don't have time to go through all of them in detail. I've picked two of them that I'm going to explain for you. They have to do with formation of our solar system and also with extrasolar planets. In the context, in general, I'm a dynamicist, and my work has to do with planet formation, planetary dynamics, and all that. I do a lot of computational simulations, a lot of celestial mechanic pen and paper analysis. And in the context of solar system, majority of my work is on the formation of Earth and origin of Earth water, but I do many other things, including dynamics of asteroids, main belt comets, comets themselves, Kuiper objects, and all. In the context of extrasolar planets, majority of my work is on the detection, formation, and dynamical evolution of the system, try to understand how they formed, whether they are habitable, a lot of work on habitability, whether they are habitable, and also a project that is very near and dear to me, understanding planets in binary and multiple star systems. I've been working on this topic for over 25 years. And this is what I'm going to explain in the second part of this talk. We have been able to discover several of these planets. I'm going to explain to you how we discovered them. So starting with a solar system, as I said, most of my work is understanding how terrestrial planets form and how they acquire their water. This type of simulations you're familiar with. These are traditional models of terrestrial planet formation. We have a bunch of planetary embryos, several thousand planetesimals. The with or without giant planets, we let them interact with each other. They hit each other. As they hit, they stick to one another. They grow. Water goes from one object to the other. And at the end, we end up with a bunch of planets, a bunch of asteroids, and things of that sort. I deliberately chose a simulation that doesn't produce solar system, just to emphasize that this type of simulations are stochastic and they may not result into what we want at all times. Now, the issue with these simulations is that they consider collisions to be perfectly inelastic. When the objects hit each other, the code merges the two objects to one another and then adds the masses and their water contents and then uses the simple conservation of momentum and moves on. But in reality, however, collisions are different. Collisions are of this sort. When objects hit each other, they shatter each other into pieces, they fragment each other. There are fragments that increase the number of the integrating bodies, and also there is debris that is produced, there is dust that is produced that goes away and removes mass from the system. And sometimes objects, the collisions get to the core and remove mantle, disrupt core. Sometimes they don't. And depending on what type of collision they are, the water or chemicals may transfer from one to the other, or they may be wasted during the collision. Some water may evaporate because of the heat of the collision. Some water may recondense back onto the objects. Some of the debris may get reaccreted and all. This is what I've been doing for past 5-6 years, trying to basically make models of terrestrial planet formation more realistic and getting closer to a type of model that could make predictions. I'm working on mechanism of collisions and the details of when two objects hit and produce fragments and debris, how material from one goes to the other one, how much material is wasted, goes away, how much material stays, how many fragments are produced, and try to put that in the context of a more realistic collision model. I have projects going on with this, proposals going on currently, and we'll see how they all turn out. In the context of extrasolar planets, my focus has been for past 10 or 15 years, my focus has been on understanding, detecting, characterizing planets with multiple stars. Kepler telescope gave us that capability to detect these type of planets. For many, many years, people like myself have been saying to observers that planets with multiple stars exist and they can form formation models and theories support their existence. But technology had not reached to the level to detect them. And with Kepler, we were able to detect them. And the very first one was Kepler 16. It was a circumbinary planet, a planet that goes around both the stars. And that opened the door to discovery of many more of these objects. I'm going to explain quickly how we detect this. And you can see the process and the way that the whole mechanism works. So consider this system. This is a double star. You see the star and a planet that I'm showing with dashed line. Now, what I want you to see is that as the system moves, the stars get closer to each other. So one star goes in front of the other and blocks the light of the bigger star. We can detect that blocking. And then the star comes out and the planet starts going. So now you see that the planet the second star goes back behind the bigger one. So now it blocks the light, the bigger one blocks the light of the smaller one. We can detect that one as well. Now watch what happens with the planet. The planet goes in front of one star, blocks that light. We can detect that blocking, and then the planet comes out and then blocks the light of the second star. We can detect that one as well. And eventually the planet goes away and everything goes back to that. So with all this, we end up with 4 types of light curves. One for when the primary star blocks the secondary star blocks the primary star, one for when the primary star blocks the secondary, one for planet in front of the primary, one for planet in front of the secondary. And you see all of them here, what happens. And we use this and model or create a model for the system and then run that model until we get the best fit. And that's how we come up with our detection. We have been able to detect 13 planets through this process with Kepler, and several of them have very nice features. If you're interested, ask me about them and I will explain in the Q&A session. With tests, however, this doesn't work. I'll explain in a second. But before that, I see the slide that I have here. Most of these planets happen to be Jupiter-sized and close to their host binaries, which to us suggests that they must have formed at farther distances and they migrated to the current orbits. They cannot form in the current orbits. The reason is that the perturbation of the binary is very strong and it doesn't allow the region around it to be hospitable to planet formation. So these planets must have formed farther out and they migrate inward. This is another project that I'm working on currently. It's a project that I've been working on for several years, but and I have an active grant that is working on this, trying to smooth out this process and understand it in detail how the migration works. And like I said, with tests, however, this process doesn't work because with Kepler was sitting on 150,000 stars, and with 100,000 stars, 150,000 stars, and is watching them all the time for 4 years. But Kepler only sits on one region of the sky for only 27 days. And we will not have enough the transit to actually detect planet unless we are lucky and in one observation, the planet can transit either of the stars a couple of times, like the cartoon that I'm showing here. If the planet transits the primary and secondary within that 27 days, then we can have it detection. So this is going to be the topic of my lightning talk. We have detected the first planet like that with tests. We are very happy about it. The paper has been submitted, is under review. And that brings me to the last slide. Many of these planets, they are in the habitable zone of their binary systems. And about 4 of them are in the habitable zone of binary second. They are binary stars. They are big. They are too big to be habitable themselves, but they could have moons that could be habitable. That brings me to the end of my talk. It was very good talking to you all, and I'm available to answer questions during the Q&A session. Thank you.